All right, part two of this. So quickly, the last few things. The energy level diagrams help with the Bohr model. So the Bohr model explains those spectral lines. So when we look at the energy level diagrams, things to remember. You have the level that it's jumping on the left-hand side. N1 is the ground level closest to the nucleus, right? And then you have your ionization up here where your electron actually leaves the atom, right? And so things to remember as you have electrons that are falling down closer to the nucleus, they are emitting photons, right? They're emitting energy. As an electron tries to go up energy levels, they have to absorb a photon. So they have to absorb a certain amount of energy to move up the diagram. They're going to emit a certain amount of energy in the form of a photon as they go down the diagram. Right? And so calculating the difference in those energies comes from this relationship on your reference table. The other thing to remember here is that these energies are given to you in electron volts. And there is a conversion to convert from electron volts to joules because we need energy in joules when you use any of these equations like E equals hf. So to convert from electron volts to joules, you're going to use the relationship 1 electron volt equals 1.6 times 10 to the negative 19 joules. Okay? So the energy here needs to be in joules. And then the very, very last thing was the Standard Model and the particles that are found inside the nucleus. Right? So protons and neutrons are made up of smaller particles known as quarks. There are 6 varieties of quarks. So we talked about all 6 of those very quickly. They're on your reference table. Up, down, top, bottom, charm, and strange. And you combine those quarks to create a whole number charge, right? So it can be +1, it can be -1, it can be 0, right? Elementary particles, but it has to be a whole number. So for example, these are 2 you should know. A proton is an up and a down, and a neutron is an up and 2 downs. So if you look at combining those charges together, you get +1 for a proton, and you get 0 for a neutron. Other particles of the Standard Model are leptons. Again, there are 6 varieties, an electron, a muon, and a tau, and each of those has a neutrino counterpart. Neutrinos have no charge. So the example you need to know of a lepton is an electron. All leptons, the electron, the tau, and the muon, have a charge of -1, right? But neutrinos have no charge. Okay? For all of these, they also have an antiparticle, right? So each of these has an antiparticle as well, and the antiparticle has the opposite charge. Right? That's your key here. So for instance, an anti-electron would have a charge of +1 elementary particles. Okay? And then finally, our classification of matter in the Standard Model. So all matter can be broken down in either a lepton or a hadron. And leptons are something that we just talked about, right? So an example here is an electron. If it's not a lepton, then it must be a hadron. And hadrons can be broken down into 2 ways. You have baryons, and baryons consist of 3 quarks. And again, these are things that we've talked about, right? So a baryon would be 3 quarks. Here's your examples, a proton and a neutron. Right? So example here is a proton, also a neutron. If it's not a baryon, if it's not made of 3 quarks, then it must be a meson, which is made up of 1 quark and 1 antiquark. Right? So again, you want to make sure that you understand how to read those charts, understand how to classify matter, and that is your year in physics. Right now, there are some things that we did talk about further than this, but they would not be tested on the Regents exam. So what I recommend you do is kind of review this, Go back to anything in your notes that you need to, and then try a practice Regents exam to see how you would have done.